we can get started. Today we're happy to have Lina and Necib from Caltech. She studied at MIT with Jesse Taylor. She did a lot of work on dark matter detection both in neutrino experiments and the Galactic Center. And recently she has been working more on grinder data sets such as LSST, Gaia, and the hopefully upcoming MSC. And today she's going to tell us what you can learn about dark matter from the Gaia data. Please.
Okay, so thank you so much for having me. I'm very excited to tell you about what I've been kind of thinking about over the past couple of years. If this picture doesn't make sense now, it's okay. It will later at some point. Okay, so basically the whole overarching goal of what I've been trying to do is to have the local map of dark matter. And by local map, I mean the local phase space distribution of dark matter. And you can understand why this is intricate because, well, we haven't seen dark matter. And answering this question is actually very timely, and it's mainly because of the evolution in two things that we have, in particular simulations and data. So starting with simulations, cosmological simulations have had quite a bit of progress lately. They used to be just like these boxes where you have dark matter particles, and dark matter would just like form these overdensities, and then related with filaments, as you can see here, and then you would basically stop there. That's what dark matter only simulations. But lately, we've been actually able to track a lot more properties of the baryons, and in particular, we can start with the temperature of the gas, which you can see here, and this is really important in stellar formation, but we can also track properties of the gas, in particular, for example, the gas metallicity, which does translate into the metallicity or the chemical distribution of properties of the stars. So once we have the gas and we have the metallicities, we can go into stellar light, and we now can actually zoom in these simulations to have actually Milky Way-like disk galaxies, which has not been really trivial to get to this level. So now we can finally have the resolution and understanding of good properties of these simulations. From the observational side, we have Gaia, and on April 25th, 2018, Gaia has given us actually the data of 1 billion stars, the kinematics of 1 billion stars. Here I'm only showing you a small subset of 96 million moving over a period of 800,000 years, and you can see them here, from the kinematics that we got from the second data set of Gaia. So basically, mixing these high resolution simulations with the Gaia data is going to finally enable us to actually have a better understanding of the phase space distribution of dark matter. And it will really tell you why we should care as the talk goes. So before that, let's try to kind of rewind and try to understand what was the status of the field. So dark matter is kind of, we think about it as this overextended halo. This is where we are, and in particular, we live at the edge of the galaxy. We are at about 8 kiloparsecs from the center. The galaxy extends 10 kiloparsecs. We're part of the disk. It rotates at about 220 kilometers a second. And we live in this huge halo that is about a factor of 10 in density. Now, if we look at the velocity distribution of dark matter locally, we can see that it is actually, or we have been assuming that it is a Maxwell-Boltzmann distribution for a very long time. And this is actually what we use up to very recently. Now, what I'd like to do is actually go back to understand where the Maxwell-Boltzmann distribution actually came from. And it all comes back to rotation curves. So pre-1970s, we thought that our galaxy looks like this, where the rotation at the center is a lot faster than the rotation at the edges. And as I just mentioned, we live at the edges. Then with the work of Vera Rubin and Ford in the 1970s, we realized we actually live in a galaxy that looks a lot more like this, where you can see here that the edges are rotating almost as fast as the center of the galaxy. So said another way, this is the flat rotation curve, where here is the distance from the center of the galaxy, and on the y-axis we have the rotation of the stars, and you can see here that with the mass that from only the stars and maybe even the gas, you would expect it to actually fall as a function of the distance, but it is actually flat. So if you are a physicist in the 1970s and you're facing this problem, you have kind of like two ways to go. Either you change the laws of gravity, and some people have done that, or you're going to change the gravitational potential that your stars are actually swimming in. So the simplest thing that is going to give you a flat rotation curve is that of an isothermal sphere. So that's the simplest potential that you can get, a non-rotating, isotropic, isothermal sphere. This is what what we've been calling the standard halo model, where the circular velocity is a constant, sigma here is the velocity dispersion, and it's just one number. The mass density is isotropic, it goes as 1 over r squared, which when you integrate, you end up with the enclosed mass as a function of the radius that grows linearly with r. The reason that I show this is because it makes particle physicists very, very uncomfortable, because nothing should grow linearly with r. There has to be some kind of cutoff, something has to happen, and it makes people nauseous. So, if you kind of put that away, and you're like, okay, let's just stick with this, apply Poisson's equation, you'll end up with a Maxwell-Boltzmann distribution. So this is the Vinny-Tremaine formulas. Now, we have to actually kind of pause and think, what are the assumptions that actually got us here to the Maxwell-Boltzmann distribution? Well, we had to assume that our system is in equilibrium and it's isotropic. And of course, the question is the Milky Way really in equilibrium and isotropic? The answer is no, otherwise I wouldn't be asking. Let's pretend that was some suspense to this question. So, if we take a look at this simulation, the dark matter halo looks a lot more complex than the spherical black sphere that I actually put earlier. It actually looks like it has a lot more structure. So, the density and the colors here tell us about the density in the dark matter. Here is the host halo, so this is where the galaxy is going to live. But there are also a lot of different structures and a lot of different subhalos. You can see here that some densities I call subhalo and some I call dark subhalo. And the reason for it is that if I overlay the stellar density, now we're looking at the stars, we'll end up with some structures that will have a stellar density associated and some of them will not. So again, this is the actual galaxy. So at this point, you might look at this and you're like, well, okay, this is what your simulation looks like. It might not be what reality is. Well, we turn to this longitudinal sky survey and we find the field of streams. So basically the northern sky in SDSS looks like this, where there's a lot of overdensities. You can see here, they're related with streams. So this is the GD1 stream, this is the Orphan stream, Sagittarius is a huge thing, and Path 5 is over in the corner. Now, you might wonder, okay, why do stars do this? They're not supposed to be just like randomly aligned. And I'm going to focus on GD1 stream, Sagittarius, and the Orphan stream, and try to figure out how they come about. So, this is the Milky Way, and these are 3 different dwarf galaxies that just have fallen into the Milky Way potential. The fact that there is a gradient between the 2 sides here, a gravitational gradient, makes it that this dwarf galaxy is getting stripped in slightly different ways in the leading arm and the trailing arm. Which means that these are actual large structures that you can actually see in the sky, and that will lead to maps like the one I just showed. Now you might ask, well, these are what the stars are doing. What you're discussing is the dark matter, so what do I care? Well, these dwarf galaxies actually start, just like the Milky Way, at the bottom of the potential of one dark matter halo. If you assume that the dark matter is collisionless, just like the stars, the dark matter is going to get stripped in a pretty similar fashion. And once you get here, you know that, first of all, this is definitely breaking spherical symmetry, so this is not an isotropic system, and it's also not in equilibrium because these are actually transient states. At some point, all of this is going to be virialized and you're not going to see these beautiful structures in the sky. Which means that the Milky Way, in dark matter, is not isotropic and it's not in equilibrium. And what I really want to point out, actually, is that these are not just random events. This is just how galaxies form in general. They're very cannibalistic, so they just swallow each other and get bigger. Okay, so now, how do we actually map out the dark matter? We're not going to say, well, everything we believed in is wrong, have a good day, and then we just move on. There might be a better way of actually doing this. So for that, I have a 3-step program where from simulations, I'm going to correlate the kinematics of some of the dark matter to some of the stars. Some is a word, very important word that I did not write on purpose, and I will discuss further. Then once you establish that dark matter traces some of the stars, you can go into the Gaia data, measure the phase space distribution of these stars, and then go to 3, empirically obtain the local phase space distribution of dark matter. So step 3 is a lot harder than it looks, but we'll get to that. So let's start with the simulations. How can we correlate the dark matter and the stars? For that, I'm going to use FIRE, which stands for Feedback in a Realistic Environment. And here I'm going to show you a very sped up version of how a galaxy forms, and all of these are, the entire light is just stars. What I'd like you to focus on is how many mergers actually do contribute to this. So you can see here that that's one, and this is actually one of the quieter galaxies that we have. That's another one, and then towards the end, it actually at redshift 0, it ends up being a more or less disky Milky Way like. But of course, that was sped up for a reason. Let's try to kind of break it down into different merger stages, because this is how I like to think about it. So first, we have a merging galaxy, where the stars are at the bottom of the potential well. This entire object is just falling into my main galaxy. So far so good. Second thing, as that starts to be getting stripped, we end up with a case of streams. And this is actually from the videos that I just showed. Now, there is a third stage that a lot of people don't really think about, and it's that of debris flow. So debris flow is actually where the stars and the dark matter are pretty coherent in space, but they still have velocity structure. The way I'd like to think about it is if you have a long distance race, and a lot of people are running, they start in one line, but after some time, somebody is like ahead a lap, somebody is behind a lap, so you don't really see that beautiful structure that they started with, but they all have some similar velocity with some dispersion. The same thing happens here. There is some velocity structure that has not been washed out yet, even though you can't really tell when you look at the stars. So in order to understand the correlation between the dark matter and the stars, I'm going to focus in my simulation at location close to where my sun would be. So basically, a distance from 6 to 10 kiloparsecs, very close to the disk. So this is actually, you can think of it as a donut. And I'm going to look at the stars and the dark matter that have been accreted in that region. So we start with the most boring case, where these are old mergers. So in this interval, again, I'm looking at the accreted stars and the accreted dark matter. It's a simulation, I can cheat, I know where they come from. And now I'm plotting in spherical coordinates the histograms in VR, V theta, and V5 of the dark matter and the stars. Since these are old mergers, I'm defining them at everything that has merged in before redshift 3. So this is very, very, very old stuff. So first of all, the dark matter and the stars have similar kinematics, and that's very encouraging. But the second thing that I really would like to point out is that these distributions look Gaussian with a similar dispersion in VR, V theta, and V5. And indeed, if you put these together, you will end up with something that is very close to the maximum Boltzmann distribution. And this makes sense because these mergers have happened a long time ago, and they have had since enough time to actually be colored. Excuse me. But again, this is the boring case. We're going to go to slightly more interesting things. If we look at dark matter and stars coming from more recent mergers, in this particular case, this is a merger that has been brought in at redshift minus 0.9, redshift of 0.9. Then, again, we're only looking at the stars and dark matter from one merger in the solar neighborhood, and we find that the dark matter and the stars do track each other quite well. And these distributions do look different from the previous ones from the older mergers. So I would like to actually focus on the radial distribution over there. And there will be a reason for this. So first of all, there is this double peak structure, which I call, I started writing this Lovi structure, and then somebody just raised their hand to tell me that Lovi is not a word. So now I have to actually write that out of principle. But this double peak structure actually has a reason. So you can imagine that if you have a sphere and you're kind of shooting an arrow through it, and that arrow kind of does a 180 and comes back, so something very, very eccentric orbit, you'll end up with as stuff coming in, you'll end up with a peak and negative velocities, and as stuff is coming out, you'll end up with the other peak. So this particular signature is really kind of a remnant of a very specific type of orbit and a very specific type of merger. And again, you might say, well, these are simulations, who cares? It's interesting, and you start to care when the same thing actually shows up in data. So to kind of rewind that same merger that I was just showing, and to actually show the correlation between the stars and the dark matter. So these are the stars and the dark matter that I have in that donut that I was actually showing, so in that one, over there. And this is where the sun would be. And now I'm just going to play this backwards and actually see where the object is going. So everything starts all over the place. is why this is a case of debris flow. You can see that this is not like a beautiful stream. Everything is just, it's not spatially incoherent or spatially coherent. And then early on, you can actually start seeing the structure of things kind of go back to being a bit more stream-like, and finally find emergent object. So here you go. Now you can start seeing the structure, and then it goes back into that object. And you can see that the dark matter extends a bit further than the stars.
How big is the object?
So this object here actually has a mass of 8.2 10 to the 10 solar masses total that has merged in this particular simulation.
Which is what relative to the Milky Way?
Oh, so this is about, well, it's a little bit less than 10%.
It's like the LC.
Yes.
Could you speak up, Nick, so we can hear you
Oh,
clearly?
I was asking what the size of that object was, and her answer was that it's 10%, which I said was about the size of the Large Magellanic Cloud.
Yes. So it is a dominant or a pretty large merger in this particular simulation. Okay, so again, that was simulations. What does the actual Milky Way look like? Well, the kind of catch here is that accreted stars do not come in with a label. So we need to figure out how to disentangle the stars that actually came in from mergers from the stars that are just born in the Milky Way. So this is what the Milky Way looks like. Again, this is where we live. We're part of the disk, where we have the pretty young stars, but what we're looking into is the halo and any structure here in the stellar halo. These stars actually have slightly different dynamics, and in particular chemodynamics, where here, I would like to actually introduce the metallicity of the stars. So I'm not sure if everybody's familiar, but just to review, the metallicity of a star is basically the iron fraction of, so Fe with respect to hydrogen, and it is a log scale taken with respect to the sun. So Fe over H equals 0 means it has the same metallicity as the sun, -1 means a tenth, and then you go. And I want you to remember that the sun is a very, very young star. So -1, -2, these are much, much older stars. So the sun is actually part of the disk. So the disk tends to be more metal rich. So these are stars that are much, much younger. So you should think of the age going down as the metallicity goes up. Okay, so let's start with this, where on the x-axis here I have the vertical distance above the midplane. On the y-axis I have the metallicity. So disk stars, almost by definition, tend to be within the disk. That's why they extend up to 2 to 3 kiloparsecs. Versus accreted stars, because they just merged in from elsewhere, they're not confined to the disk, so they just kind of go through in and out of the midplane without being constrained by it. And that's why they extend a lot further. And they tend to be more metal poor because they've been born a long time ago and then they were brought in.
Excuse me, astronomers argue that the accrete population is a thick disk, so you're throwing in the thick disk with our disk.
Yes, right now I'm thinking what I think the disk is thin and thick disk. Yes, that's right. So here we can also look at the rotational velocity of these particular stars. Again, disk stars tend to be more metal rich, and almost by definition will rotate with the disk. And of course, the thick disk will rotate a bit slower, but these are technicalities. The disk is going to rotate here. While accreted stars, they come from whatever which way, so there shouldn't be any mean rotation. It's just that there will be just a very, very large dispersion, but it should average out to 0. So the metallicity of the stars really tells us also about the origin of these stars. In particular, for example, there is a mass metallicity relation that relates the mass of the stellar mass of a particular object, and in particular, for example, dwarf galaxies, all the way up to larger galaxies. And on the y-axis here, I have the average metallicity of the stars in that particular object. So what I'm trying to say here is that the metallicity of a group of stars can tell you a little bit more about the origin of that particular object. So basically, to summarize, we're going to use the chemical properties and the kinematics of these stars to figure out if they're accreted or if they were born in the Milky Way. Again, the reason that I want the accreted stars is because they brought in dark matter with them, versus the stars that were born in the Milky Way have nothing to do with the dark matter whatsoever. They're just telling me about the dynamics of the initial gas of the Milky Way, which is not what I'm interested in. So now we're going to go into Gaia and actually measure one slide, Gaia is awesome. Gaia was launched in December 2013 with the goal of giving us a positional measurement and the proper motions of 1 billion stars. Again, we got pretty much, we really did get this in the second data release a year and a half ago now. And the 1 billion stars is 1% of the Milky Way. This is the largest kinematic catalog to date. So I'd like to show this here because, so this is the sun and this is the extent of Gaia with some accuracy. And the circle here is really not, it's not just to show where the sun is, but it is with the previous experiment, which was Hipparchus, so it ran from 1989 to 93. This is the extent of it. And again, I showed this and everyone was like, Hipparchus was a great experiment. And I'm like, okay, I'm not saying bad things about Hipparchus, I'm just saying Gaia is awesome. So, out of Gaia, we actually figured out the Gaia Enceladus. So Enceladus here, this is a Greek god who is the son of Gaia. And this is a merger that has happened about 10 billion years ago, somewhere between redshift 1 and 10. Unfortunately, you probably have heard it, or you will only remember it by its other name, which is not as cool, which unfortunately is called the Gaia sausage. Because Vasily Belukharov apparently was very hungry, I don't know. So this is the most significant merging event in the solar neighborhood that was discovered last year with the Gaia data. It has a stellar mass of 10 to the 8 to 10 to the 9 solar masses, so 1 to 10% of the Milky Way, quite large, and fell in somewhere about 10 billion years ago. I'd like to actually show the Gaia sausage because it actually tells us a bit more about the properties of this merger. This is the sun, we live at the edge again. So the merger is going to be here in the red stars. It has happened about redshift 1 to 3, and you can see it pulling in. It gets a bit screeny very quickly, but then it gets kind of turned to shreds pretty fast. And then there is this kind of extended, elongated structure. So these orbits tend to be very, very eccentric and very radial. So this is how the Gaia sausage actually ends up. So now that we have the Gaia sausage, what would I do? Well, I know that some of the accreted stars are going to correlate with dark matter, and I know that there is a big merger. So what I do, I just go and actually did the first kinematic modeling of these stars. Unfortunately, only 1% of the stars in the disk actually tend to be accreted, which means that the disk is a complete nightmare for me. It's 99% of my data, and that's not what I want. So first thing, and I swear it gets better towards the end, I do the first dumb thing, which is I'm going to mask the disk and look 2.5 kiloparsecs above. I will still have some disk component, in particular a thick disk component, but still this will make my life a little bit easier. So I took Gaia VR2 data, cross-matched with this longitudinal sky survey here, and what I did is actually fit basically a bunch of Gaussians for the disk, the halo, and the substructure. The substructure is the Gaia sausage. In VR, V theta, and V5, so again, spherical coordinates and 3D kinematics, and metallicity all at once. So actually, interestingly enough, we did the exercise before including the metallicity, and there were quite a few degeneracies, but once you include the metallicities, everything kind of falls into place, and everything converges nicely. So let's try to kind of go review and make sure that the distributions that I'm getting actually end up being exactly that as expected. So first of all, there's a disk component, which is here. This is in green. And you can see here that it actually peaks at about 180 kilometers a second. It's rotating, has a net V5 rotation as expected. And it's also peaking at very high metallicities, at -0.7. Again, this is what you'd expect from the disk. Now we look into the halo. So the halo is isotropic, so very isotropic component. It doesn't have any net rotation VR, V theta, or V5. And pretty large dispersion, they're almost similar. This is what I really refer to as a very, very old component. And it actually has a peak in metallicity at -1.8. So this is a group of isotropic old stars. Now there is one more component, which is that of the double peak structures, the structure here in VR, which is then associated with the Gaia sausage. And this is really when things get really cool. So it peaks at metallicities of about -1.4. So it is older than the disk, younger than the halo. It's telling us that it is a more recent merger. And the interesting thing is that it contributes about 60% of non-disk stars. or 60% of the accreted stars. And this is quite a bit of a large fraction. So you would expect it to have brought in quite a bit of dark matter, not 60%, as I will get into. But this is really interesting. So to kind of summarize, I've seen simulations where in mergers I end up with this, where we have this double peak structure from very specific type of merger. The dark matter and the stars do follow each other. And then going into the data, we find something that also has this double peak structure, not exactly the same. But we expect the dark matter to be doing the same thing. Or at least if dark matter was cold collision with dark matter. So now let's try to understand how to get the local velocity phase space distribution of the dark matter. The biggest catch that we got here is that these mergers do not contribute the same amount of dark matter as they do stars. Which means that when I said 60% of the non-disk stars are coming from the Gaia sausage, that doesn't mean that 60% of the dark matter is going to be doing the same. And the reason for it is because there are, you can think of it, for example, as like dwarf galaxies have a lot more dark matter relative to stars versus much bigger objects have a very different ratio. In order to deal with that, we needed to figure out how to rescale these numbers correctly. So this is now the speed distribution. So we're not looking into particular components. And I'm going to have a component from the halo, which is what I'm referring to as the relaxed old component, and I'm going to have a component coming from the substructure, or the Gaia sausage. To get these factors here, I end up using the mass metallicity relation that I showed earlier in conjunction with abundance matching. Basically a relation that tells me, that relates the metallicity of a particular object, because I know the average metallicity of the stars from the sausage, to the ratio, the mass to light ratio. And that way I can rescale the fractions from stars to dark matter. And I find that the substructure actually contributes about 42%, with pretty large error bars, as you can see. So this is the speed distribution. And you can see here that this is the halo in red, the substructure is in blue. We put them together and we end up with this speed distribution here, which is quite different from what you would assume in the standard halo model, which is the line in gray and dashed here. So this is interesting, and it actually has quite a bit of ramifications. But there's a huge caveat that I really need to mention, which is this does not take into account anything that doesn't have stars in it. Which means, so remember early on when I said there were subhalos and dark subhalos? So this here is not the full distribution of dark matter, because there will be a component coming from smaller objects that do not have stars in them that I cannot figure out this way. So there is a huge missing component, something I'm working on. But we really need to estimate the fraction of these disrupted dark subhalos and how they affect the speed distribution in order to end up with a full phase-space distribution of dark matter. Putting that on hold for a second, how does this affect dark matter direct detection? Well, review of dark matter. That white thing, this is a xenon atom. This is dark matter, appropriately colored. Then they come in, interact with each other, and produce some scintillation light. This is the Lux experiment, and this is a xenon-based experiment. So this scintillation light is later detected, and that's how we know dark matter is there. The interesting thing is that this process really does depend on the properties of the dark matter.
Which experiment was that?
Sorry, this is Lux. Yeah. This process does depend on the astrophysical properties of the dark matter, and in particular, it does depend on the velocity of the dark matter. The way you think of it is, basically, it tells you about the energy of the dark matter particle, and the more energetic it is, the more scintillation light it's going to produce, and the easier it is to detect. So when you see a plot like this, which you've seen probably a million times, where here is the dark matter mass, on the y-axis the dark matter nucleon scattering cross-section, everything above this black line here has been excluded by the Necib091019v2 experiment. This line has already in it the velocity distribution, and it has already in it the Maxwell-Boltzmann velocity distribution. Unlike the local density, which people disagree on as well, where it just everything kind of goes up and down, this does change the shape of the distribution. And in particular, it affects like this line, whether or not it goes this way or this way. Interestingly enough as well, it does affect different experiments in different ways, which means that some experiments that you might think are the ones that are most constraining in particular areas might not be the case. So for example, if I were to just scan over my error bar, for example, just to make it a video because I got really into videos, and look into the rate as a function of the energy, you will see that this is the expected rate versus this is the one that you would have expected had you assumed a Maxwell Boltzmann distribution. Which means that if you put it on this style of plot, you might end up with this, this inner model is going to constrain this, and the velocity distribution I showed you is actually going to be a lot less constraining. This doesn't mean that this is really the final thing about velocity distributions, because again, I did say that there is a missing component. I'm just saying that assuming a Maxwell Boltzmann distribution is really we might end up ruling out more parameter space than we really should. Of course, I really need to point out that this depends on like the easiest kind of scattering process, and there are actually some studies looking into effects for different scattering processes. But okay, are there any questions so far? I know I talked way too fast.
So by any chance, can you go down to 1 GeV dark matter by using any hello model, any velocity distribution?
Can you go to 1?
1 GeV dark matter
With
for the direct detection. That line
Wait,
cuts out.
this is basically with a xenon one time.
Right. So for example, okay, do you have any velocity model where one can go down to 1 GeV?
So I think you would if you get your distribution to be, if your distribution is going this way.
Yeah,
but
right.
actually we're ending up looking at slower distributions. So we're going the other direction.
Is it a possibility?
I mean, it is possible. We still are missing a component. If all your dark subhalos are like live here, I'm still working on that.
Actually,
So
I'm sorry,
go ahead.
Actually, so this is editorial. I actually saw a preprint of a recent paper that they did some modeling by Christina Vessel.
Oh yes,
Where
yes,
she
with the
was
LMC.
claiming basically the Large Magellanic Cloud brought in the highest speed particle to the solar neighborhood. This hasn't been published yet, but she actually does has a story where there's that high energy tail is very populated. I forgot what the limits are on the top of my head, but it does strengthen things at very low mass.
Yes.
So it's like it's not completely impossible.
So the LMC is not on its first orbit by the
The
way?
It is, but yeah, I read
Yeah.
Christina's paper. So it is on its first encounter. It's just that its halo extends all the way to us, and even though the fraction is actually very small, I think 0.5% or something, most of the dark matter particles end up living like right here.
Yeah,
Even
the density
small
of
fraction.
LC particles is very
Yeah.
low, but the velocities are very high in the frame.
That's why, yes, it might be possible. And it's not the end of the story yet. Okay, so there are two large caveats, right? Like one, which was we're missing the dark subhalos. Two, what I was doing earlier, I was just masking the chunk of the disk. So you might say, well, you know, all the distributions that you found might be just way above the disk, and these are not actually close enough. So they might be biased, or you might be missing something. And this is where things kind of get really fun. So again, only 1% of the stars close to the disk are treated. And when something gets really, really difficult, you just make a computer do it. So working with Brian Austin, we actually have a machine learning algorithm where, you know, basically you teach a machine, this is what a cat looks like, and it learns from that. And then you give it a picture like that, which, honest to God, for a while I was waiting for it where to land because I didn't know that was a cat or a dog. It said it was a dog. And love your dog. Basically, once you actually teach it what something looks like, it starts picking it up, even if it is in a pretty difficult situation. So what do? Well, we can make mock catalogs out of the fire simulations that I showed, teach that to a computer, and then land with an accreted star catalog. So unfortunately, I need a worse picture of Gaia because to kind of trick people. This is the simulation, this is a real Gaia, but I will find a worse Gaia picture, or I need to improve this one. So, because it's very easy for people to guess, and I stopped asking people. Anyways, this is an unfit. It was led by Robin Sanderson, and basically it is a mock Gaia catalog of 3 of the fire simulations that we have. And what we end up doing in this project with Brian is we train on this, we're actually giving it the 5D kinematics. So the position in the sky, the parallax, proper motion, and our ray attack. And then of course we have to resample a couple hundred times to scan over the errors and do everything appropriately. At the end of this, we end up with an accreted start catalog that you guys should email us if you want to play with it. And then I can look very, very close to the position of the sun, and now I can look at my stars. So Brian just made when we were working, Brian made this catalog, sent me a bunch of stars, and he was like, I don't know what I'm looking at, have fun. I was like, cool, let's do this. So first thing, plot all the sets that I have. So here again, we're back to spherical coordinates, VR V5, VR V theta, and V theta V5, and this is very close to the sun. So what do you think of the structures that are really neat to find unless something really bad happens? Come on, this horribly made.
I didn't quite understand the question. Can you repeat it?
Yes. So I've been given a bunch of stars that are supposedly accreted from the machine learning algorithm. What are the actual kinematic structures that I really need to find in my catalog to make sure that my catalog is really working as prescribed? That was the question.
Guessing like where in the free space do this?
Oh, what object should I be looking for?
Sausage.
The sausage, thank you. The sausage has to be there, otherwise something really bad happened. And indeed, you can kind of see it by eye, this double peak thing, which you give it to any clustering algorithm, you will find that this is the Gaia Enceladus, this is the halo, all the way in the back. The Gaia sausage does not have any net rotation, so V5 is 0, V theta is 0, everything's cool. But then you look at it a little bit more and you're like, wait, what is this? This is not supposed to happen. And, or at least like, I didn't know it was. So then a lot of people tell like scientists, oh, it's Eureka movement. It's mostly, let's be real, all of us, we just have the, oh my God, I have a bug moment. So 3 weeks of me sitting on this, not telling anyone, and trying to figure out what is it. Then I was like, well, okay, if you find something, you name it. So I got to name something. That's pretty cool. So this is actually what I'm trying to introduce you to is the Greek goddess of the night. They're called Nyx. So let's take a look at the 500 stars that are most likely to be associated with things. This is what they look like. So these are little arrows. This is the position of the sun. This arrow is the arrow of the motion of the sun. And you can see that it is kind of like a wave of these stars here, and in this plane. I'm going to focus on one of the planes to actually zoom in a little bit more. And you can see here that these are the Nyx stars. In the background, I plotted some of the disk stars that are actually in my sample. And you can see that the Nyx stars are actually pretty different. And indeed, they actually have quite a bit of higher velocity, and they're rotating at an angle.
But that's how you picked them.
I'm sorry?
That's how you picked them, right? So
I picked, yes. So basically, I picked stars that have a non-trivial kinematic structure. What I'm trying to argue is that these are not disk stars. These are something else.
but the disk star is going to have a small proper motion, so you've already selected these stars that have higher velocities and proper
That's
motions.
right.
So you wouldn't expect there to be any correlation with the disk, because you already pre-selected it against the disk.
Yes, but this is, but this is, again, for an argument against anybody who says, well, you know, your machine learning one is gonna, like your machine learning is doing something funky, and you're picking out funny disk stars. They're not. But yes, you're right. They have nothing to do with this. So, interestingly, these are 13% of the local, local accreted stars. The sausage here is 72, so the sausage actually is within, within range. Earlier it was like 60 above the plane, now it's 70. And the halo is 15%. So basically these Nyx stars, which are not anywhere else, so that we just found, have a non-trivial fraction. They have very coherent velocities. And we now actually can even look at their chemical properties. Of course, we only have a small subset of spectroscopic data from these stars, but this is enough to actually see that, okay, well, they're peaking at -0.5, sorry, with lower enough magnesium values. So this is most likely accreted, a bunch of accreted stars. If you look at their age, they actually match they match isochrones in about 10 to 13 gigayears. This is not a fit of the isochrone. These are just like me plotting some isochrones and actually finding that everything fits. We have a couple stars here, so I'm not actually cheating. So, the thing is, to get these stars in the beginning, what the machine learning actually is giving me is a score associated to each star. And the score is 0 if the star is a disk, 1 if the star is accreted. Of course, it's not just zeros and ones, it's the whole spectrum. So it depends on where I put the cutoff. It tells me about the purity of my system. So, which means that if I take a score of larger than 0.95, which is what this is, so these are the more, like the stars that the machine learning algorithm is really, really certain are accreted, I'll end up with these stars. I can always loosen this cutoff a little bit at the expense of getting a little bit more discontamination. And when I do that, I end up with another structure here, which we cross-checked and has the same chemical properties, the same eccentricities. It's just that so we have one of the structures that goes this way, another structure that goes this way. And interestingly enough, we have a simulation example that does the same thing. Basically, one of them is like on the first orbit, and then it does this and then that. So, interestingly enough, NICS, this is a new structure, and we're arguing that it is a remnant of an accretion event, a pretty large one in the disk. It dominates the stars, or at least it doesn't dominate, but it is a large fraction of the stars near us, very, very close to us. And it has very interesting properties. So there are a lot of different things that we can do here. And in particular, we need to correlate how much dark matter is in here, dark matter between stars, how to correlate the dark matter of stars and streams. You can see that earlier I was talking about very old mergers and I was talking about debris flows. I did not correlate the dark matter in streams with that of the stars. And the reason for it is that the process is still getting started and the tidal disruption is still kind of going underway, so there is a bit of phase, a phase or a spatial decoherence or like overlap in between because the stars are in the bottom of the potential well and the dark matter extends a bit further. That makes it very hard to actually correlate the dark matter and the stars properly. So, one of my very large to-do lists at this point is to do that, because we really need to understand how much dark matter is coming in with NICS. And we need to understand, we need to do further observational study of the stream to understand a lot more properties. So for example, out of 500 stars, I only had about 80 that had their metallicities, and 30 of them only had both the metallicities and magnesium measurements. And we really need to understand how much dark matter is bringing it with it. So there are quite a few questions. Thankfully, the story doesn't end here. We still have quite a few things planned. And in particular, we have the LSST, which will start in 2023. It will give us proper motion for much, much fainter stars, so we'll have a much larger catalog, which if we combine with MSE, and this is a spectroscopic survey, is going to give us the radial velocities of stars down to 100 meters a second, error bars that starts much, much later. We are going to end up with much, much larger catalogs that will enable us to really understand not only galaxy formation, but also how this kind of implicates a lot of the dark matter. So, to conclude, because this is way too fast, from simulations, we could correlate the dark matter in the stars, and in particular the dark matter in the stars from mergers. What I really would like to emphasize here, though, is that, and this is kind of some disagreement that we had with other groups, is that we're not saying that all stars or all the stars of a particular type are going to correlate with all the dark matter. We're saying that stars and dark matter from the same mergers are going to correlate with each other. And then to actually be able to build the velocity distribution, or the phase space distribution in general, you have to actually not only get the velocities correctly, but also you have to rescale them appropriately, taking into account the fact that dark matter and stars do not contribute the same ratio. So from simulations, we correlate the dark matter and stars. From Gaia, we can measure the phase space distribution of these stars, and then we can put them together to end up with at least like the beginning steps of the local phase space distribution, which of course we still have one missing component that we're still working on. But I'd like to leave you with discovery of all, which is that I'm not so bad at Photoshop. And this is Gaia coming, this is Nix. That's a Gaia coming out of the Milky Way. So, thank you.
Thank you, Lina. Any questions for the speaker?
Yes.
F of H minus 0.5 is a strange metallicity.
Yes.
And so what sort of object do you imagine came in at that metallicity?
So, okay. So for example, some patches of Sagittarius actually have metallicity minus 0.5.
Yes, but they have a really unusual S process on this.
Right.
So that'll be easy for you to check.
Yes, once I have more spectroscopic measurements. So the minus 0.5 is a bit, it is a pretty funny one, and it also makes, at first we were worried, is this too big of an object that has merged in, what happened there? What I think is going on, or at least like, I think that there might be some non-trivial metallicity gradient that we don't see, so that's why I wouldn't take the minus 0.5 too much